All right, everyone, welcome to another life science session at the Wolfram Institute. Today, we're going to be coming back to infrageometry. We've had a few meetings with Stephen in private, and there's some new directions that we want to explore. So today, we're going to be mostly kind of reshaping and deciding on these new directions, and also reviewing the priorities that we have and see what we get from some brainstorming, and so that I have some starting points to go off of in the next few days. So yeah, let's go. I will share my notebook here. All right, make it a bit bigger. Is that okay?
Yeah, that's good.
What are we on? 120. Can you go 150?
150 is a bit too much. We'll click.
That looks good. Yeah.
Finish it fine.
Cool.
Okay, so super fast recap for everyone who's unaware of infrageometry. We are trying to get features of differential geometry, features of continuous geometry out of discrete models, and doing so by not approximating the continuous case, but by recovering it in a sort of statistical limit. That's the essentially new kind of direction that we want to take. So we had a few meetings with Stephen that basically meant that we were going to redefine a little bit the direction. So let me just bring up the notes very quickly. So yeah, as I say, we want to develop a kind of statistical view of geometry where the objective is to try to find some infrastructure that will limit towards something that resembles continuous geometry in some large limit. And the reason why this is slightly different from not approximating continuous geometry, because one could think of what is the difference between that and, say, using triangulations or meshes of surfaces and things like that. Well, the reason is that we begin with no space at all. So our starting point is spaceless. So geometry is completely disembodied. All we have are discrete combinatorial structures. And the expectation is that out of only combinatorial features and discrete computational sort of processes, we might get something like geometry out of it. So for those of you who have followed the project before, this is a slight deviation from what we were trying to do. There's an aspect of this project that we might revisit in the future, but for now it's sort of relegated to a second tier of interest, which is the idea that discrete sets, discrete data structures like hypergraphs could be treated themselves as sort of geometries of some kind, and what kind of adjustments one would have to make in order to make a sensible framework out of that. That was our main direction previously with infrageometry. Now, after some reshuffling of priorities in terms of what we want out of this project and what Stephen wants to work on immediately, we are going to be working on more of the statistical angle, so to speak. So trying to define things that at least plausibly are reasonably well-defined geometric-like structures from purely combinatorial principles, and then try to see large n limits to some degree to see if something like geometry emerges from it. So to that end, we are going to mostly actually restrict ourselves to graphs instead of general hypergraphs. I mean, there's no immediate reason not to use hypergraphs, but the reason why we want to use graphs is that there's a bunch of techniques and concepts that are very clear in graphs, essentially the fact that you have paths as your general universal measuring rod, that you have a lot of counting mechanisms and notions that depend exclusively on moving on graphs, and the fact that you have a metric on graphs always, and you have geodesics and you have all these discrete notions. So with so we are going to try and just with graphs sketch out a lot of the concepts that that one wants to see in geometry, right? In this sort of notion. So another simplification. So that's one thing, one point to keep in mind. We're gonna keep graphs as our main object here for spatial graphs. So I'm actually going to update this just to represent that. And the second point to keep in mind is that we are going to approximate local functions with numerical distributions on nodes. So if you were listening to Infrageometry live streams many months ago, you might remember, almost a year ago now, actually, you might remember that this is how we began, that we wanted to consider functions as numerical distributions on nodes and possibly edges. We abandoned that because there was a problem on how to assign those values and what values to assign to begin with and so on. So again, in the interest of sketching a lot of possible constructions instead of getting into detail, we are going to now consider those kinds of definitions of functions. So these considerations should be considered these kinds of limitations should be considered kind of the constraints that we impose ourselves to see if something can be found based on the relatively high amount of evidence that the metric structure of graphs allows for a lot of things like neighborhoods and geodesic balls and all these kinds of things. So our objectives in sort of the near future of this project should be Stephen mentioned a few, and we all had our preferences, but I basically identified 3 milestones that would be good to have. So one is 2 homology, and I say 2 homology instead of just homology in general, because if we understand 2 homology, we understand homology in general. Obviously, that means understanding 1 homology in the process to get there. So 1 homology should be relatively easy to understand, because this is just paths in graphs, and this is something that there is quite a bit of literature written about it, and arguably we should find a lot of algorithms that already do that. Understanding 2 homology is going to be more challenging, especially if we restrict ourselves to graphs. But that's one thing. So that's one of the things I want to sort of brainstorm today. Second thing is product structures and fiber bundles, and perhaps more generally the notion of mappings, what some people usually refer to as pullbacks and push forwards of in the category of smooth manifolds. So in more pedestrian language, this means you have a manifold, you can map from it and into it in many different ways. And so understanding surjections, understanding injections, understanding sub-manifolds, understanding eventually fibration structure, product structure, and things like that. So this is with the ultimate goal to understand things like fiber bundles and sections of bundles and things like that. But since we first have just motivation to look at spaces, I think having a target to understand product structures, like the Cartesian product of 2 spatial graphs, whatever that is, that'll be a good milestone. And finally, we want to understand some notion of symmetry, right? And symmetry transformations. So naturally, differential geometry is all vertebrated by notions of symmetry, of course. One could even think that, I mean, when you go to the summary here, let me see, yeah, the concept maps, I think. these are some. Where do I have this? Yeah. So in things like a principal bundle, you have notions of the diffeomorphism, groupoids, groups, and transformations, and things like that. So when you look at this kind of textbook summary of contents, you see that Lie groups form a pretty big part of this whole story, and imagine vector bundles with all the associated constructions also do. So anyway, so that's the third milestone. I want to get to something to do with symmetry, something to do with a space that transforms into itself. Stephen mentioned this as rotational symmetry. I mean, I don't know how much we can get something like rotations in this context, but we'll see. I mean, we do have a metric structure, so maybe there's some natural notions of isometries of that. But yeah, so that's basically our goals. So let me just say here, 3 main goals, just as a recap. Oops. We have homology. We have, let's say, spider bundles. And we have symmetry transformations. And maybe this is also understood as leaders. Okay, so what are the, I mean, are there any comments, questions at this point of, because I just tried to summarize how we're going to refocus on this project in the coming weeks.
You just don't forget about functions.
Functions, yes. I mean, yeah, I mean, this, you mean the mappings between the spaces?
Like having a scalar field.
Yeah, I mean, those things are more constraints than goals, because Stephen did say, just think of those as assignments of values at edges or nodes. So those are the games. I mean, so let's put it this way, right? So there's this, and there's constraints that we have are so we're dealing with spatial graphs, not hypergraphs, to begin with. We are we have to exploit the metric structure, which as you can imagine, is the fact that in any finite graph between 2 points, between 2 nodes, there is a shortest path length, right? Not necessarily a shortest path, but there's a shortest path length, right? So that's the metric, that's the distance function in any finite graph, right? And then the other constraint is functions as numerical value assignments. Again, and this could be both nodes and edges. And yeah, no existing embedding space, and obtain geometry like features in large cardinal nodes. All right, so that's kind of a summary of where we are. So we can have a few of the things that we already developed. So I basically adapted some of the functions that we had, some of the graphs from the physics project. We can use as benchmarks as well. I don't know how relevant the places idea is going to be anymore, because this seemed to be, I mean, this was really important for the whole hierarchy edge situation where you had ambiguities on how to deal with adjacency. In the fact that the moment you have hierarchy, your adjacency is a multi-valued statement between, or at least a hierarchy statement between different nodes. Now, adjacency is a purely pairwise statement, and therefore edge places might not come as so relevant. We might still want to think of them, especially when we think of functions and value assignments and things like that, but I imagine that we are not going to have to deal with a lot of these things. So I imagine we might want to use still this adjacency coarsening. So this is a notion of basically defining hypergraphs on top of graphs, right? And I think neighborhoods are going to be hypergraphic. So again, the constraint is spatial pairwise graphs, right? So that's the spatial graph. So that's the starting graph. Doesn't mean that we cannot define hypergraphs from it. So the hypergraphs, in this case, you can see, for example, if I apply, let me see, what is this? All right, so let's say spatial graph is this one. Let's take the adjacency. This let's take the coarsening of that. So as you can see, what this is doing is taking the, I mean, if there's just a binary edge between a pair of nodes, it just stays the same. But this function is going to look at every node, and it's going to create a edge for all the nodes that are adjacent to it, right? So yeah, you can see, for example, clearly 9, 2, and 6 here. There's a ternary edge there. You can see, for some reason, do I see? Can I do it this way? I put, yeah, for some reason, 7 and 1. Is that an edge?
No, one is connected to 7, 3, 5, and the other one. And 2.
Yeah.
So there's like an arity 5 hyper edge between all those. Including 1, I think.
No, sorry. So 7, so 8 is only connected to 7. That's why we have a binary edge here. 7 is connected to both 8 and 1 only, right? So, but I was not seeing it. But if I zoom in, this larger, you can see there's a very thin thing there. That's a ternary edge. Right? If I draw, I don't know if this is gonna crash. Well, it did. Let me see if I can draw this now. Aha. There you go. just fixed it. That's great functionality with the draw, Nick. Amazing. So yeah, so very easily you can see that this hypergraph is built by the adjacency relations. So in a way, you can think of this as the neighborhood hypergraph. Of course, we should, if we actually want to define this as the neighborhood hypergraph, we should make the edges somehow typed in a way that distinguishes the center of the neighborhood, right? Because right now this is just 7, 8, 1 as a completely unordered edge. But anyway, so this is an example of, we can still use hypergraphs and get there. So just graphs will get there. So yeah, this is old stuff. Let me just get rid of it. And you can see this. I just wanted to show this part. What is it? No, this spatial graph. So hopefully we're going to see, yeah, you can see what happens here. So every time, I mean, this function still considers hypergraphs, so it still takes the adjacency information from the next step. So first step is no change. Second step is just applying the adjacency coordinating here. So these are the neighborhoods. Second step basically takes, it just applies the same function here, right? So so you would see that actually why. Oh, right. Yes, of course, because now, right, there is this ternary edge here in 1, 7, 8, and that is extending. And then after a couple applications, then we're just getting an edge between all the nodes. And then, of course, you get as many edges as there are nodes. So anyway, so this is just an example of that. It will be interesting to, what was it called? WM1. Interesting to have a look at the, yeah. WM1. Let's get rid of this. I don't know how long it will take, but probably a few seconds. And yeah, so this is what we oh, there it is. So it's just a new hypergraph made of all the neighborhoods of the previous ones. Oh no, sorry, that's the one. Yeah. So WM1 looks like that. And oops. Yeah. And that's the adjacency corseting of it. So anyway, that's just an example. So I think what we should do is, so all right, so this section here on paths and curves is kind of ready to go. This is what I developed basically as a prototype example, but now that we actually have sort of direction from Steven to focus on just doing graphs, it has sufficient functionality. So this is a set of functions to deal with directed paths on graphs, right? So the way this works is, you know, if I have something like a graph like this, I can specify a directed path simply as a list of directed edges, right? And so the order of this list actually matters. That's part of the sort of embedding of the curve in the space, so to speak. So if we want to see that, you want to see in this graph this particular path that goes from, what is it, from 1 to 4, then to 4 to 1, then to 1 to 2, then this is the function that does it, right? Like we just evaluate this. It's kind of an abstract directed graph on its own, but then when we do pathing graph, we can just see it within the graph itself, right? Then we can represent several paths in the same one. We can compose them, and this is the usual construction with paths of path compositionality. We, of course, I mean, this is the idea, right? So let me see, path 2. So path 2 is 1, 2, 2 to 3. Path 3 is 3 to 2, 2 to 6. So one can go path 1, then path 2, sorry, path 2, then path 3, right? Because you go 1 to 2, 2 to 3, 3 to 2, 2 to 6. So this should compose to a path that just goes from 1 to 6 eventually. So if I do indeed, these two are the paths, right? So you see path 2 is 1, 2, 2 to 3. Path 3 is 3, 2 to 6. So I define path 4 as the compose of both. And then when I show the path in the same graph, you can see that it has this. So this is lacking some visual cues. Maybe we can sort of like draw a dot in the beginning of the path, and then draw kind of a big arrow in the ending of the path or something like that. But basically, you can see go from 1 to 2, 2 to 3, then come back, then go to 6. And so that's the composite path. Now, the reason why we go through all this trouble is that we want to have a computational and purely rewrite-based approach to homotopy. So this is something we saw before, but now I want to sort of recap it, and then we can think about how to do homology more generally. So what is this exactly again? Oh, these are the same functions, I think. Yeah. Oh yeah, this is just copied from the above. But there's something quite different. We have two. So we now have a special kind of object, which is a graph with directed graphs on top, right? We have the spatial graph as the kind of ground truth, then we have sort of sprinkled directed edges on top. Very simplistically, one can just deal with this as two types of edges instead of, but generally one will have to label and keep track of things. So if we imagine we have this spatial graph, right? This I kind of made by hand to illustrate a point. If we want to go from 1 to 7, we can see that there are several paths that we can take, right? We can go 1 to 4, and then 4 to 3, and then to 6, and to 7, and so on. So yeah, I mean, these are just some functions that we need to turn things into a hypergraph. Yeah, and so this function basically finds the possible, so given a spatial graph, finds between a source and target nodes, and given a maximum length, it finds the paths that exist between them, right? So for example, here I have between 1 and 4 directed paths of length up to 2. You can see there's only 2, right? You can go through here or through there, right? Because you are constrained to have length 2. That's why you only find 2. But if you say up to length 3 now, then things are a bit different, because you can basically cross the edge in the middle and still get there, right? So you can go 1, 3, 2, 1, 1, 3, 2, 4, or 1, 2, 3, 4, or just go in those directions. So, and of course you have the lower ones because that's the maximum. So here, what I did was consider two paths in the same graph, right? So out of all the possible all the possible paths that can exist, I defined two of them, and we understand that these are homotopy equivalent, right? Because intuitively you see vertex 1, vertex 7, you see a bunch of stuff in the middle that is connected, and then you see two paths that are distinct that go through the same sort of jungle of edges in the middle. So the idea is that that connectedness should feel like filled in space between the two paths, right? And that's intuitively, that's clear, right? Like you can see that going through 2 or going through 5, you leave space behind somehow. And so my idea was, let's use these two rules, homotopy compose and homotopy deform. So homotopy compose basically means that if you have a path between 1 and 2 and 2 and 3, you have a path between 1 and 3, but only if there's space between those places, right? So I hope that this is clear from this pattern over here. Actually, give me a moment. I want to, Nick, we should really, just as a side comment here, we should really make it default in the Packlet that the rule, that the embedding on the right-hand side kind of takes the default embedding of the left-hand side, right? Just for clarity.
Uh,
I mean, I understand it's not the most general. I understand
I'm
there's
not sure whether you
reasons
can generalize it. It's like I don't know, it's not. It has to check the actual vertices if they match. Then you can transfer the embedding from one to another. I don't know.
Yeah. No, I understand there's more layers to it than that, but I think I haven't found an example where I didn't want that yet. So just give me a moment. I'm just finding the, here we go. So I use this function here. Not here. And I just change. That should be the trick. There you go. All right. So, so yeah, as you can see here, I mean, even more explicitly, I could say that's okay. Yeah, you have a spatial graph chunk, so it's a triangle of undirected edges, and you have a path that goes from, say, 1 to 2 to 3, right? And then what you want to say is that if there is space between 1 and 3, then you could shorten your trip and just go directly from 1 to 3, right? So what I wanted to say before is that I can just, where is it? Right? So if there's space between 1 and 3, I can go directly between, if I went to 2 and then to 3, I can go directly to 3, right? But that's why the rule involves like 5 edges here and 4 edges here. It has a bit more information so that there is more context. So it doesn't just apply blindly to only directed edges, which would be the typical rule, you know, this kind of rule that I have here in this other notebook. No, this is the typical sort of transitive closure rule, right? Like you have a, yeah. Sorry, what was that? Was someone asking a question?
No, I think
No,
that's all.
Oh, okay. I heard something. So this is the typical transitive closure rule. So you have 1 to 2, 2 to 3, and then you just go 1 to 3. But of course, this rule will apply in this situation, right? Like if I applied this rule to this hypergraph, I would get this hypergraph because it just doesn't care about the existence of these other undirected edges. But if I applied this rule in a graph that didn't have this edge here, or indeed didn't have any of these 3 undirected edges, it would still apply. And that's what we don't want, right? We want to say, like, there was a path from 1 to 2 and 2 to 3 because there is a chunk of space between them, right? There's an undirected edge 1, 2, and there's an undirected edge 2, 3. And then only in that case, when there's also an undirected edge in 1, 3, that we complete that path. And that's why I call it homotopy compose. Maybe it's not really homotopy compose, it's really just path compose or something, because it or spatial compose or something, because it's really only composing if there is spatial edges in the shortened path, so to speak. But then more importantly, we do have the homotopy deform, in which case this is really homotopy deform, that minimally does something like this, right? So in a sense, it doesn't change the path, it just wiggles it, right? So this thing really is somehow shortening the path. It's like when your thing wiggles, you can sort of collapse it and make it shorter, but you can also wiggle it, right? This is the idea of wiggling the path. Now that I think about it, it might be necessary to also implement the sort of the inverse rule to this. Let me just write it for the record. Let's path compose here, and let's call it this path. How do you call it? Bulge or something. And then I am basically just going to change the hypergraphs. Right. Yeah, let's call this path compose. Let's call it shrink. I think that's more clear. All right, so I hope this is clear what's happening here, right? Like if we are thinking about the idea of homotopy, right? I hope everyone remembers, this is the idea that you have two points in your space, you have curves between them, and as long as there is space between these two curves, you can deform them from one to the other. Basically, without this more mathematical way of thinking about it, is that if you give me 2 points in space and a curve between them, if there is indeed space around this curve, then you can wiggle the curve and still a curve, right? That's kind of the idea. So we are trying to capture that with discrete rewrite rules. So path shrink, I think, is an obvious one, right? As I said before. Now path bulge is the inverse, and the important thing here is that because we are wiggling things, this should be reversible rewrite rules, right? So the inverses should be implemented. So interestingly enough, homotopy deform is its own inverse, right? It's a quote unquote idempotent rule, right? Which is an interesting thing, actually. Because if you notice, this graph and this graph are isomorphic. They are not the same graph, but they are isomorphic. I mean, crucially, they are not the same graph. If they were the same graph, then it would be the identity rewrite rule and it would do nothing, right? But these are obviously isomorphic as graphs. And therefore, when this pattern on the left-hand side applies and rewrites to this pattern, then it then can apply again, because it is just basically you only have to do is you have to swap the names of the, so let me bring this in harmony with the other two, right? So notice that the only distinction between these two graphs is the rows of 2 and 4, right? So 2 and 4 are just flipped rows, and therefore I don't have to implement the inverse rule or the reverse rule, right? In this case, a path shrink and path bulge are also sort of inverses to each other, right? Because the input graph of one is the output graph of the other. So in combination, these two, they would create cycles in our rewrite system, right? Because shrink applies, then bulge applies, shrink applies, then bulge applies, shrink, right? And then we get the cycles. And so the cycle has basically a length 2 word associated to it, which is shrink, then bulge. However, the form has a length 1 word associated to it because it's just the form, and you're always cycling on the same state, right? Okay, so what's the point about this? Well, maybe we do a slightly different experiment today because we have a new rule. So the point is we want to get these rules here should really be a bit lower in my notebook. So yeah, they should be here. So we're going to take these path shrink, path bulge, and homotopy the form. And we're going to apply them to these initial states that have some paths in some spatial graph. Okay, so for that, I'm going to use these functions here. So unfortunately, the colors are not preserved. But so what am I doing here?
Richard made a comment in chat about involution.
Involution, that's what it's called. Yes, that's the technical name. So an involution, an involution is exactly something that is idempotent. Wait, do I want to say idempotent? No, I want to say nilpotent. So this is a slight. This is a kind of a bit of a technicality, but just to be precise. So idempotent means idem means same, right? So idempotent means that something squares to itself, right? And so the idea is that homotopy the form squares to identity, right? So identity is usually referred to so like the zero, additively speaking, right? Like nil, 0, so nothing, and so the do nothing rule is what the sort of nil rule is here. So you would call these. So you would call homotopy the form nilpotent, right? Because it squares to do nothing. However, bulge and shrink, they are just inverses of each other. They don't have any. I mean, in fact, you could say that in an atomic sense, they are as far as possible from being squarable, right? Because you can do shrink squared, right? On itself, right? There's just no way that you can match the output of either of these with the input, right? Anyway, that's an interesting conversation to have about sort of tracelet analysis and whatnot. So here, this is interesting. So here I just use, so did I define, what did I do here? Oh yeah, so what I did here was I take this graph, which is, homotopy graph 1, homotopy graph 2. So let me actually run this. Ooh. Oh yeah, I need this. I need the paths and just what? I changed some names, I think. No, it's strange. That is very weird. What's happening? Is it just, oh, maybe I didn't run that actually. Yeah, that's right. So yeah, so these are, okay, those are unfortunate random colors. Those are better. So yeah, these are the two graphs with the two paths. And the idea here is that if you rewrite this path on the blue path sufficiently many times, you would eventually find something that looks like the homotopy path here, right? The green path, basically. I mean, you could think that both are being rewritten kind of in a full way, right? Like you generate all the possible futures, which is finite, of course, because these are finite graphs, and we have two rules that are conservative. Notice that the rules themselves, so they are below. The rules themselves are conservative because even if directed edges are being multiplied or reduced, are being reduced or generated, the undirected edges are conserved in all cases, right? So these are conservative rules. It means that we know ab initio that we have finitely many future states in both these rewrite systems. So the kind of mathematical way to go about this is to say, take one path, generate all the state space of the homotopy transformations, meaning shrink, bulge, and deform, and then take the second path, do the same thing, and if there is one common state between the two, then they are homotopy equivalent, right? It's mathematically it's very transparent what is happening. Intuitively, it makes sense, right? Because intuitively you can instead of just doing that, intuitively you can say, well, if I take one and I apply, the rules in all possible ways, and I can get the other, then it means that I can deform one into the other, which is what it means to be homotopy equivalent, right? So that's what I did here. I took the first state, and then I applied only homotopy deform. Why? Well, because I prepare things by hand, right? I know that if I want, so both are length 3 paths, and these two rules change path length. So I would only be adding noise to the system if I just added these two, right? I can still add them, and we can see how it looks like. Path bulge and add, what is it? Compose. I mean, this is going to be much bigger. So let me run only couple generation. Yeah, this is going to be much, much bigger because it's going to move things from 1 to 6 to, maybe actually it's not that big because there aren't, actually might be, yeah, right. So it isn't that big. So
is there an easy way to highlight the path in red?
I think so. I'm just because these are hypergraphs. I don't know exactly how to do it. I don't know if Nick is has a quick way of, because I mean, with graphs there's like built-in options and functions to do that, but this is the rewriting kind of overrides
Well, just
the
edge style, right? You just need to change edge style. What's the difference?
yeah with
If-
style.
What?
I didn't hear you, sorry.
I mean, you just need to change the edge style, whatever you want to highlight.
Yeah,
You don't need any like extra functionality. Just
yeah, no, but what I mean is that for example here the only, like, the rewriting is just undoing the style. So should the rewrite rule, like, I mean, for me not to like go and apply a style option or something to each output graph, I could just include something in the rewrite rule that basically preserves the styles or something, right?
Yeah, it's possible, yes. It can preserve annotations.
Yeah, but I just didn't want to do it because it was going to be just a local hack for this case and whatever. And this is just a point of illustration, but surely that's easy to do. Like it's no big problem. Okay, so you can see some of so let's see, for example, what happened here. So clearly this was a bulge. So which bulge exactly? So this was 1, 2, 6. Then 1.
I mean, technically 1 to 2 can be bulged out to 1 to 3 to 2 kind of thing.
Oh, sorry, no, these are after 2 rule applications. Yes. So what happened here was there was a right. So there was a homotopy deform to take 1, 2, 2, 6 into 1, 3, 3, 6. And then, because that's a bit confusing to see, but that arrow here is going from 1 to 3, right? So it's 1, 3, 3, 2, 2, 6, right? And then, so that was the first rule I applied was the form to go from 2 to 3, just basically push the path to pass through 2 to pass through 3. And then there was a bulge, right? Because there will be a path that will go 1, 3, 6. And instead, this is the path that goes 1, 3, 2, 6, right? So that would be bulge. That would be bulge applying to the edge 3, 6, right? So anyway, I think in 2 steps we don't get there, do we? What is 5? Yeah, the path is through 5. So yeah. So as you can see, this is two aggregate 2 rule applications. So 2 bulges, shrink bulge, and so on. Also, out of curiosity, we should see the same path again. Let me see where it is. Oh, here it is. Is it? Yeah. This is cool, right? So this is the same path again, right? We have 1, 2, 2, 6, 6, 7. Wait, is that right? What is going on there? Oh no, that's right. This is just 2 being curved here. Yeah. So what happened here? Why do we get the same path? This is the path we started with. It's because, I mean, could be 2 reasons actually. We should get 2. That's interesting. So this one is probably the form applied twice, right? And we could also get one that does bulge and then shrink, and then shrink and then bulge. So we actually, yeah, there's another one. Actually, this I think is the one that does the form twice. This is probably shrink bulge, and then there should be a bulge shrink somewhere here, right? So these are good reality checks, right? We have 3 graphs that are the same, which correspond to the cases in which these things compose to be identity, to do nothing to your original graph, right? But the point that we are trying to illustrate, we are not quite there because we wanted to deform the blue path into the green path here. So for that, we need to push the thing all the way to 5, to vertex 5, right? And this is not very clearly embedded here, but this you can see as, I mean, let me see if I can. Oh no, this is an actual, what? This is a graph. I think those are graphs. And these hypergraphs, why can't I draw them?
I need to run the program to edit that, right?
Wait, I need to copy it out somewhere?
Wasn't there a separate program to manually edit the locations of the plot?
No, but I could just right-click draw. But I guess. Nick, do you know why? There's no.
I don't know. You turned into graphics somehow. I don't know. What's the code? Those are graphics, not hypergraphs. You can
Oh,
tell
are
by
they?
the hypergraphs have this magenta like.
Yeah,
border.
I know. But I didn't know. I didn't. I mean, I do run a hypergraph in the end. This graph here is a hypergraph. And I'm just doing hypergraph addition.
But hypergraph addition doesn't return hypergraph? Really?
It does, right? Yeah, I'm confused.
Your graph, your GRPH looks like graph, not a hypergraph, no?
No, this is just the. Oh, maybe actually. Oh, wait. No, but this plus here is definitely a hypergraph. Like the graph here. So this is a hypergraph. This is clearly a hypergraph. But somehow when I put the thing in, I mean, it's okay. I just wanted to. So this is a hypergraph. Sorry. I just wanted to illustrate this.
Yeah, move that to the side.
Yeah.
Kind of.
That's much nicer.
Yeah.
So just wanted to, whoops. Have a much nicer, because I mean, some people might be thinking, what kind of example are you even using here? Looks very Baroque, but it's a very natural one, right?
So here we're saying that the path from 1 to 2 to 6 down to 7 can be homotopied to the path from 1 to 3 to 6. Because the path from the intermediary vertex 2 is connected to 3. So you could scoot it down, right? Incrementally.
That's right. So
right.
I'm going to try and rerun this. What? Huh. I think it's just overriding the. It runs, yeah. Yeah, I think it's just overriding the embedding for some reason. Anyway, but yeah, but I'll just bring this here for visual clarity. So this is the graph, right? And the two paths are the blue and green paths are the 1, 2, 6, 7, 1, 5, 6, 7. So basically, there's some interstitial space between them, some edges. And so you can see that by arbitrary combinations of shrink, bulge, and deform, you would need minimally 3 bulges to get to 1, 5, 6 from 1 to 6, right? So in this generation, because this is only 2 rule applications, that's not enough. So let's do 3 and see what happens. Now it's taking longer because obviously there are many more. So you have all this. Oops, it's crashing. Nope, it's just.
Oh well.
All right. So we have a lot of them, but if everything goes according to plan, the last one should be, yeah, the right one. So the last one is apply the form 3 times. And so sure enough, we get 1, 5, 6, 7. Right. So, but of course we get a lot of more noise in between, right? So this is a good illustration. Just for a second, I'll reduce the zoom, just to kind of visually represent what's going on here, right? So this is a good representation of what's going on, right? So the final state here is the same state as the red one, right? Like this and this. We start with this one, that's this state. And after all these rule applications, we get that, right? So I wanted to bring this example with a lot of detail because this is kind of the paradigm that we are going to go after, right? It's not only that we get homotopy in some kind of statistical limit where we are approximating space, but the way we compute is going to be something like this, right? It's going to involve applying discrete rules that just kind of move things around. And I mean, in this case, these two rules are very intuitive, right? Like we understand. I mean, that's why they have evocative names like shrink and bulge and deform and so on, because they clearly correspond to the intuitive thing that we want these things to do, right? But anyway, so we find that, and the way to formally verify it, so we can just collapse the way to formally verify it is that we take this as and we canonicalize it. So we just we represent it with just an abstract relabel hypergraph. And then we take the final state that we thought was the same, and we actually indeed check these two are the same. So you can see that this is the final state, right? The output of the rewriting. And don't we have the function already?
Or what?
Isomorphic hypergraph?
Oh, it's in the not really. Maybe. Yeah.
Isomorphic hypergraph Q, isn't that?
Yeah. Or you want the actual isomorphism. If you yeah, I think if you just to check, that's the one.
This is the one, right?
Yeah.
I can take the initial state here, and this will give me true. Yeah, there you go. So yeah, as you can see, this isomorphism thing is not taking anything like labels or colors or any annotations into account, which is exactly what we want. So anyway, as part of today's brainstorming session, it'll be great to think about how we go for two homotopy for this. And so basically, what are equivalences between surfaces? I mean, more to the point of what are surfaces to begin with in this framework. So yeah, anyway, this was a good reminder that everything works and we have a framework. So
yeah, cool. So it's discretized sort of rewriting rules that capture homotopy information.
Yeah. So this, in my opinion, kind of settles the question of whether we have homotopy in our system, in the sense that, you know, we could now take a triangulation of a torus, and we could actually find curves that are homotopy equivalent. Actually, what is a quick way to do that? I mean, maybe we can just do that for right here, like. What is a good way to do that? I just need to extract the mesh of a torus. And then just make that into, just take the edge list of that and.
Oh, of
and
a
then,
torus, you're saying.
of a torus, yeah. Just as the quintessential example of a closed surface. Like non-trivial closed surface.
Yeah, it would be like discretized region. I'm not sure. But
And Nick, do you know a quick way to do this? I feel like I'm just missing the function names because all I need to do is generate a torus at the surface, which I'm sure is in some kind of data in the language, and then just need the edge list of the mesh.
I think there's even a torus graph.
Okay.
But you can try discretizing the torus itself.
Torus graph, there you go.
nice.
Let me see what this does.
It's just an MN, probably.
Oops.
Parameters like grid graph, except that there's gluing on the edges.
I was just checking on the documentation and I need an update. I can.
We don't have much time.
Yeah. Just gonna render this. Oh, I see. Interesting. So I have to say is maybe 5 by 5. Interesting. I guess if I make it bigger, it's not going to make it any clearer. Well, actually, yeah, kind of.
Do a 3D embedding, do graph 3D of that.
Oh yeah, it does. It does make
It's
it
totally a torus.
It does make it clearer. It's larger. Okay.
So make them different. When you make them the same, it's not. You have to
Oh
make
yeah, because that's the length of each. Yeah. Well,
the other
that's
way
okay.
around.
I mean, should it matter?
That's
All
a
right.
lot better. Cool.
Okay, maybe a bit smaller. Yeah. Okay, yeah, that's nice. That's a nice graph. So this would be a good test to, for example, identify the fundamental group of a torus, right? So one could imagine just doing paths here, and if we have I haven't implemented it, but it's easy to implement a cycle where it just checks that the path is closed, and then you basically take 2 cycles and you demonstrate that they can be deformed to one another or not, right? And obviously this can be very computationally expensive, but because the deformations are finite, you can actually definitely say that 2 paths are homotopy equivalent or inequivalent in this graph, right? Oh, what I'm seeing though, interesting. Huh. What I'm realizing is that our rules will not apply to this graph.
Because it doesn't have its diagonals connected?
Exactly. Yeah.
Right.
So this is only for kind of triangulation triangulated.
Right. So like this rule is sort of, or the one that is sliding one path to, I guess the deform rule is, it needs that middle point and that 2-length path to be able to slide over to its new deformed position along an edge that exists. So, the other way to think about that is in homotopy, what you actually need is that whole like 2-dimensional area between those two paths being filled in with material. And for hypergraphs, we can consider two paths, and there's a question of, is the union of all the vertices of these two paths included in some higher arity edge? If so, then there's material in between and you can deform.
Right. So there's this triangulate mesh, which, if applied to a torus surface, will give us.
So they'll turn the quads into triangles. They'll put one of the diagonals into those configurations, but not both of them. So it'd be like kind of ad hoc which way you can slide things around.
Yeah, but when it's triangulated, it doesn't matter. Like, it looks like a choice from, if you go from this graph to the triangulated one, but if you begin with a triangulation, it's basically unique up to size. Meaning, sorry, it is unique for every size, right? Like, if you give a number of vertices, you have a unique triangulation of the torus.
No, it's certainly not unique, but
anyway, but yeah, but that's basically the gist of it. So I think we have to go to another event ourselves, so we can stop here. But it's a good starting point.
Mm-hmm.
That's great. Can we publish this notebook for each iteration so that people can carry on and also play with it?
Sure.
We'll do it on the description for those who are watching the, we'll share the link just after the video. Cool. That was great.
All right.
Thanks for tuning in.